so that they're characterized by M1 and M2. So M1 equal to 0 would be the first row. So this is along M2. So M2 takes on values from 0 to infinity. Similarly here, M2 takes on values from 0 to infinity. Now, what happens is that when you look at, so there are two simplifications that happen. So if suppose you are looking at the first row, so there are infinite number of equations in the first row. In the first row, from the block, so let me just write down the external block again for reference. Because we are expanding around this point, we are expanding around u equals to 0, v equals to 1. You can explicitly show that the first row is, it looks like u to the power delta minus L by 2. So this is the external block. And this is not the most important piece. The important piece is going to come. 1 minus v to the power L, and then times hypergeometric one. So this is true in any event. So this is the sorry, this M1 is not there. So M1 is 0. M1 equal to 0. I'm looking at the first row. So what is this telling us? It's telling us that suppose I was looking at, say, this entry. Then only the spin 0 contributes in the S channel. There could be all kinds of spins that contribute in the T and U channel, but at least in the S channel, only the spin 0s contribute. Same story here. So if I'm looking at M1 equal to 1, then again only spin 0s will contribute because L is even. I'm considering identical scalars.
I'm sorry, I missed this. So what M1 was some power? How does that connect with spin? Oh, because there's 1 minus.
So there is 1 minus v to the power L.
Okay.
And so suppose I'm looking at the first entry.
So that's M1, which is U, the cathedral is U.
Yeah, M1 is the power of U, 1 minus v to the power M2 is the M2 is the power of 1 minus v.
So both M1 and M2 both multiply log. U to the power M1, 1
yeah.
minus v to the power M2 multiply log. Fine.
Okay. So suppose I'm looking at this entry, then in the S channel only spin 0s contribute. If I'm looking at M2 equal to 1, again only spin 0s will contribute because spins are equal. So
I'm sorry to stupid, but I didn't understand what the connection with M1 equals 0 and S channel.
So the S block looks like this.
Yes.
Okay. So when you put in the spectral function and integrate, this power is not going to change. 1 minus v to the power L. So this is. Yeah.
So that's M2, right?
Yes, that will be M2. So I'm going along the row.
Wait, is that row M1 equals 0 or M2?
Okay. So this row is M1 equal to 0 and different values are M2. This is a different powers of 1 minus v.
Okay. I thought 1 minus v was controlled by L. You're concluding that L is 0.
So what are the spins that are going to contribute to 1 minus v to the power 0?
Okay.
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 So it will be only spin 0 that contributes.
Yes. Yes.
What are the spins that will contribute to 1 minus v? Again, it will be only spin 0s because spins are even. We are considering identical scalars.
And what about the expansion of this F1? Does that also have powers of 1 minus v?
Yeah, sure. So here M1 M1 equal to 1, spin 0 is going to contribute. Okay. M1 equals to 2. It will be spin 0s and spin 2 that will contribute.
Because it's even.
Yes.
I see.
And so on. So it follows this pattern.
Fine.
Okay. So that's one observation.
One more thing. What about the u bar delta phi? You aren't able to match that at this.
No. So that is a common factor. So there is a common factor in. So this u to the power delta phi is factored out.
But it's not there in that group, right?
It is. After you put in this spectral function, because we chose such that actually, so there is this delta phi that comes here. So when you put in nu, then that's a common factor. So there is no further expansion. So we are not expanding in small anomalous dimension or anything like that. We are matching literally powers.
The gamma squared is exactly putting in the u bar delta phi powers.
Yeah. So there is no small anomalous dimension business anywhere here to produce logs. I mean, you could have gotten logs there that way as well, but there's no such thing. So okay. So that's one major simplification. and then so that will be the story for not just the epsilon expansion. This will be the story for anything. Okay. Now,
Just one question.
yes.
What happens to the log 1 of 1 minus b that comes from the expansion of the hypergeometric function?
There is no sorry what?
There will be log 1 minus b.
No. So logs come from hypergeometric. We are expanding around unit argument, not so. We are expanding around v equal to 0. Sorry, v equal to 1. We are expanding around v equal to
It's a
1.
small argument, so it has this Polyakov times the powers.
If we expand it around v equal to 0, then you get logs. Then it becomes important. Yes.
But why is there more u dependence than just u to the power delta minus?
I'm looking at just the first row where the power is 0. There is. So when I consider the second row, for example, it will become more complicated. It's seriously complicated. Even solving, I don't know. It's a compact closed form expression is not known. I have polynomial expressions for those anyway.
Wait, so here you have u to the power.
So this is m1 equal to 0.
So u to the power nothing.
So there is a common factor of u to the power delta phi which I factored out.
And how about that one? U to the power delta minus.
Oh, that's
so
so after
you
you
0 here, of course.
Yeah, but after you spare, so this becomes h plus mu minus l by 2. So we are considering the double pole which is at this point. So we have replaced that guy by delta phi plus m1. So this becomes u to the power delta phi plus m1, and then we are now setting this equal to 0.
Wait. So that delta is the delta of the intermediate
Scalar. So I have to put in the spectral function and do the integral over the spectral parameter. Okay. So this is in terms of the spectral parameter. This is h plus mu minus l by 2. It has got a double pole here.
Okay.
So it will produce u to the power delta phi plus m1 times log u plus a regular thing again, which is going to be u to the power delta phi plus m1.
Oh, so that is converting that into this delta phi.
Yeah. So you're doing quite many nice things at the same time. Okay. So let's focus on the first component and let's see what happens when you do an epsilon expansion. So let me tell you the story what happens there. So you start by writing delta phi, which is the dimension of the seed operator as 1 minus epsilon by 2. You can write plus phi 1 times epsilon plus phi 2 times epsilon square. And dot dot. This comes because it's d minus 2 by 2. And I'm putting d equals to 4 minus epsilon. And then you say that, so we have figured out what is the leading power of epsilon that appears in these equations.
Sorry, just to get the structure. There are two sources of these logs. One because of your new basis, and the second because of the T channel and U channel.
Right.
So this expansion here you were telling us about the T channel and U channel.
This is for all channels. I was telling you that the S channel contributes only finite number of spins. T and U channel will contribute all spins.
Will contribute. So any block in the T and U channel.
Yes.
Will
contribute to each of these entries. Okay? So you have to worry about how those contribute.
Yes.
So now you say that. So let's consider an exchange. So we'll put in an exchange scalar in the S channel. So let's put in this to be equal to n, and n will work out to be integer. So we can actually explicitly verify that. Plus delta 1 times epsilon plus delta 2 times epsilon square. So I have not actually told you anything about what n is. N could be integer, it might not be integer. Okay, so this is just a way of writing it. So then what happens is that when you look at the S channel contribution to the first entry, then and you're expanding up to some high power in epsilon, you will see n minus 2 appear. Okay? So that is telling us that the leading contribution must come from n equal to 2.
This comes in what quantity?
So when you're putting in the S channel, I've calculated all the residues. I've looked at it carefully. So there are poles that are coming from this hash of mu. There are poles that are coming from the spectral function. There are actually, maybe I should write down the poles. So the poles are at mu equals to delta minus h, mu equals to 2 delta phi minus h plus L plus 2 and tilde. So this is this double pole. This is the simple pole. Simple, double, mu equals to h plus L plus 2 and tilde. This is again a double pole. This comes from the block. This comes from the spectral function.
Where n tilde is any integer.
Yeah. This comes from the spectral function. This pole is cancelled in the S channel. So there is something that divides out. So these kind of poles don't contribute. There's exactly the same factor that appears, but you have to worry about these poles that in the TIU channel. And then finally h minus 1 plus n tilde. And then when you put in the unitarity bound, so you have to put in delta is greater than equal to d minus 2 plus L. Then this actually selects out n tilde to be equal to L. So these are all the sets of poles that contribute.
So the first one does not have an n tilde because that's an explicit pole.
This is a simple pole.
Okay, and the other guys are the gammas.
Yeah. Okay. So this pole actually plays a very crucial role. It's really important. I'll tell you the story about that. Because as you can make out, okay, the S channel calculation is going to be easy, but the TIU channel calculations are not going to be easy. There will be some cancellations that are required to actually simplify the equations. That's what happens. Okay. So then the leading contribution in the S channel will come from 2, which is expected.
So there will be a 1 over n minus 2, but there will be 1 over n minus 4, 1 over n minus 6, and all that stuff as well.
No, those are not there. So those will appear at some really sub-leading order. So I'm interested in the leading order. So what I will do is I will put in this to be n, and then I will expand. I'll go to mathematical, ask it to expand.
Leading is something in what?
Epsilon. If I expand to a sufficiently high order, what I'm going to see is I will see something that looks like this: n minus 2 squared.
No, I see. Sorry. So this is the phi square operator.
Yeah, this is the phi square. Yeah, but this is exactly what you would expect. The phi square is going to be the leading contributor in the leading exchange in an epsilon expansion. Because we are looking at this component. So when we go to the M1 equal to this is M2 equal to. When we go to the M2 equal to 2 case, then the stress tensor is also going to come in. The stress tensor with a conserved with no anomalous dimension. Although you can show us. So this is the S channel. Now in the T and U channel you do the same thing. So there will be scalar exchange as well as spin exchanges. Now what happens in this particular case is that when I'm considering spin exchanges, these spin exchanges contribute at there are cancellations between poles. So what happens is that the n tilde equals to 1, 2, 3, etc. poles cancel with the n tilde equal to 0, 1, 2, etc. poles from these four. So these cancel pairwise. So 1 cancels with 0, 2 cancels with 1, 3 cancels with 2. And this happens to a very high order in epsilon. So this is this kind of cancellation is going to only play a these kind of cancellations happen up to an order which is going to tell us the anomalous dimension up to epsilon cubed. So using this procedure, I don't have to worry about the spin contributions in the T and U channel because of these cancellations.
It's cancelling within the T channel or is it cancelling with the...
No, it's cancelling within the T channel. For a particular for each value of L. For each value of L, this cancellation happens between these pairs of poles.
Order by order in epsilon, is it?
Up to some high order in epsilon, which will tell us that these spins are not going to affect the anomalous dimensions until. So I should be able to reproduce the anomalous dimensions until epsilon cube using this procedure. These spins are going to enter the game only at epsilon 4.
So that itself highly constrains delta phi, right? Because if delta phi is some arbitrary number, then these guys have nothing to do with each other. This series of poles on the second line,
right.
This series of poles on the third line, they have nothing to do with each other.
Delta phi is so delta phi is this guy. So I could actually tell you what the answer. Yeah. So what happens is that these poles, the location of these poles are equal to each other up till order epsilon squared. So you can just put in the numbers and find out that the location of the poles coincide up till order epsilon squared.
Three by two. 2 minus half is equal to 3 halves. Half. 3 minus 2 minus 3 halves.
Yeah.
Oh, so then I'm not seeing. The 2 delta minus h is half.
2.
Forget it. Set epsilon to 0.
Yeah. Okay. So this is 2 minus. This is 2.
2. I thought h was d by 2.
D by 2, but we are in 4 dimensions.
Okay, 4 dimensions.
4 minus epsilon, right?
I see. So that's 0, and there you just got h, which was 2.
Yeah. So n tilde equal to 1 coincides with n tilde equal to 0. Okay.
Nice. This check is at epsilon equal to 0.
Right.
But this keeps happening this
Up to some higher order.
up to the next higher order.
Yeah. So,
And sorry, what were these two sets of poles? One of them was the Polyakov, the other.
so this one is the double. This is the gamma function that comes in the spectral function, which we have put in this the double poles,
Yes.
which we introduced by hand to
Yes.
for 9 asymptotics. This was there in the block,
That's good.
in the normalization of the block.
In the that Polyakov.
Yeah. So this does not affect the S channel, but it will affect the T and U channel.
Yeah. So this is some coincidence of working with a free field.
Yeah. Or yeah. Or if I consider a very large space, I mean that's another case where there will be some coincidences. Yeah, I think the large spin limit we have not actually analyzed as yet, but I think there is some simplification for any conformal field theory if you looked at these components, large values of M2.
And you were saying that these poles cancel in the T channel, but also in the S channel?
S channel actually these the double poles don't play a role, and in the S channel n tilde is 0 because n tilde controls the power of U. Yeah, I'm looking at the first component, so you can start looking at along the column, then they will play a role. So then solving the first component consistently actually tells us what delta 1 should be.
No, I haven't worked much yet. So the T channel, what does what?
Oh, spin 0. Only the 0 spins will contribute. 0 spins will contribute, so n tilde equal to 0, this double pole is going to contribute. This simple pole is going to contribute. These poles don't contribute.
Because they cancel against.
Yes. And for non-zero spin, this is also going to contribute. I mean, there's some there is an important role that these play for non-zero spins. So what happens is that for non-zero spins, the sum of this, and this cancels up to some high order in epsilon.
Okay.
For zero spins, this is pairwise cancellation that happens between these pairs of poles, and leaving us with only the contribution from this guy and this guy. So we could proceed in one of two different ways, both of which we give rise to the same results. So one is that we appeal to this result that was found by Rychkov and Tan, which fixed the conformal dimension of delta, conformal dimension of phi by just looking at 3-point functions.
Wait, so aren't you going to tell us at some point that f, the T channel little f, has this kind of expansion? I thought you were going to produce the singularities for the T channel little f, and then cancel that with S channels.
Right. So I've already produced. So sorry. What were you?
What just you got a little f in the T channel associated with some delta.
Yes.
Delta and what? Delta and
spins. Delta L.
Not even delta. This little f is an integral, right? Yeah. Sorry, I should have asked that. You chose your basis vector. These basis vectors. How many were there? Like the spectral function. Were they labeled by something?
They were. So after you do the integral, the labels are delta and L.
But you are doing an integral over nu, so delta goes away, right?
No. So there is a pole that is sitting at delta, which is the physical exchange operator.
Excellent. Okay, good. So this little f's are labeled by delta and L, and you could just take little f in the T channel and expand it in your u goes to 0, v goes to 1 limit.
Yeah.
And that has a particular expansion.
Which is exactly the same that I wrote here. It's like this.
With some known coefficients.
Yes.
Okay, and any delta and any L produces all of these with some coefficients.
Right.
Okay.
Right. I mean, this is using the blocks that I wrote down in the S and T variables.
And using all these, poles.
Yeah.
Fine.
Yeah.
Okay.
Yeah. So you could proceed in one of two different ways. So one of them is you could appeal to the result for the 3-point function using this method by Rychkov and Tan, where they got the anomalous dimension, or the conformal dimension of phi. Or you could say that I don't know, I don't care about any of that. I will demand that there is a stress tensor in the theory. So both produce the same result.
I haven't understood the logic of producing the result. What you're equating two singularities? Which ones?
So I am trying to set. So here I have contribution from S, T, and U. There's S plus T plus U contributions whose coefficients are e to the power m1, 1 minus b to the power m2 log u.
Yes.
Okay. So I'm looking at the m1 equal to 0 and m2 equal to 0. So first component.
Yes.
Okay. Then so we make the observation that only from the S channel only spin zeros contribute.
Yes. But from T and U everything contributes.
Everything contributes.
So how do you get anything out of that?
So that's what I was saying. So now you analyze what happens from the S channel. So this analysis. You expand in epsilon, and then you see that the leading contribution is when n is going to be equal to 2, okay, which is what you expect, it's phi square. And then in the T and U channel, there will be zero spins as well as higher spins as well as additional poles that come from these non-zero end tildes. Okay. So zero spins and non-zero end tildes, there is this pairwise cancellation that I was telling you that happens each in T and U channel. Okay. Up to some high order in epsilon. Okay. Which would leave so the zero spin contribution would be just the first two sets of poles.
But at every delta L.
At every delta L. Yeah. Yes. You have to still specify what the delta L is. Okay. You have to do the same analysis. You'll have to put in delta out the n plus something, and then you have to check what is the leading epsilon contribution. So the S channel, the epsilon contribution, if you do it in this naive way, using these normalizations, is going to begin at 1 over epsilon cubed.
What begins at 1 over epsilon?
This equation. This equation begins at 1 over epsilon cubed.
I see.
Yeah. So don't worry about the fact that epsilon into 0 is going to produce an infinity. It's because the coefficient these begin at epsilon 4. So epsilon into 0 is still a smooth limit.
So I have some maybe silly doubt, which is that the T channel expansion is around U going to 1 and V going to 0.
No. All the expansion is U going to 0, U going to 1.
No, I agree. But I'm saying that the T is a controllable thing around the other point, right? Where the OP is correct. Yeah. Now, of course, we are very far away from there.
Yeah.
So you have.
That is exactly the reason why you expect in the general case that all spins would contribute. That's exactly what happens if you are not doing an epsilon.
All spins will contribute, and you are going to perform that sum over all spins.
Yeah. So we have to keep all spins. So what I'm saying, what happens, why the epsilon expansion simplifies, why we're allowed to find solutions, is that so consider non-zero spins. So non-zero spins, there's a cancellation up to some very high order epsilon. So in fact, the equation is going to start off with some coefficient which you want to set to 0 times epsilon cubed plus some coefficient epsilon square plus some coefficient epsilon plus something which does not have any power. So this cancellation actually persists up to this order. So the spins in the T and U channel don't contribute up to this order.
The spins in the T and U channel.
Yes.
I see.
Only spin 0 contributes.
Only spin 0 contributes up to this order.
It's just a fact about you compute those.
Yes.
An expansion and you find that.
Yes.
Okay.
So for example, there could be some higher order spin zeros which will contribute here. So there could be 5 to the 4 or del 5 whole to the 4 or something like that. That could contribute at this order. It won't affect these two powers. This you can explicitly check. It's a simple thing.
And therefore only phi square contributes to this.
Correct. So, because of this behavior, you are you fix the anomalous dimension of or the conformal dimension of phi square up to the first two orders. So you fix it up to the epsilon square.
So the only reason these equation tractable primarily because all the higher spins can be right in the DNA.
Higher spins and all the higher operators of zero spin.
Higher operators of zero spins, yeah.
I thought those were anyway the higher order epsilon. So.
Yeah, so the higher order, yeah, so if you are interested only in up till epsilon square, then it's only phi square that contributes. The higher order scalars begin contributing at this order, the spins begin contributing at this order.
Yes, but if this accident hadn't happened, then you would have to worry about matching one coefficient in this channel
with an infinite number of coefficients at the end. That's exactly what happens if you try to do it in the usual bootstrap.
Yes.
That is the reason why the usual bootstrap fails.
Suppose you wanted to do some other CFT, wouldn't
that will do case by case. I mean, whether, for example, the Gauss-Nephew is tractable using this. We have not seen this. I mean, we have not checked it because we want to understand this completely before moving to something else.
So Ron is saying it sounds like tractability depends on expanding around the free theory.
Either free theory or some limits, I think.
Can one go systematically beyond the order that you get?
So I think it's possible to do up till this order at least.
No, but suppose I wanted to nth order. Will you at some point run into infinite number of equations or infinite number of variables, or can you always keep increasing the number of equations systematically?
We've not. I don't have anything definitive to say about that as yet, but I suspect that we need to go down the road. So I don't know what is going to happen. So if you're asking, I think there's a possibility that there are infinite number of spins that are going to contribute to this order and this order.
So suddenly you will lose control.
I have a feeling that this is just a conjecture. So if you look at the expressions for the anomalous dimension for in an epsilon expansion, there is a place where zeta 3 comes in. So you look the first 2-3 orders look like rational numbers,
and then
it's zeta 3. So I think from that order you will require.
Okay, but then you say that this is somehow like something that just works to low orders.
Yeah. The power of this is of course going to be when you consider trying to do this numerically or
okay, great.
Maybe if you can guess the solutions on the right time. Epsilon expansion is not going to. I don't think there's a systematic way of reducing epsilon or the coefficient of epsilon to the n term without a lot of work or.
No, but I don't think with a lot of work, but I just wanted to know whether there are as many equations as variables. Whether in principle there were enough equations to determine all of them.
Yeah. So there are enough equations up till order epsilon square to do the following. You can look at all the components around the first row, and that actually tells you that the exchange operator are going to be these double field operators. So the double field operators look like phi, del mu1, del mu l, phi. And you can actually check that you can do this calculation explicitly that you get equations which can be written in 2 lines. And you can determine these delta 2s, which are the anomalous dimension of these double field operators. These anomalous dimensions work out to be exactly what you would expect from field theory. And you can also work out these C delta L's. And C delta L's, after doing a further step, matches with the mean field theory equations. So you get a couple of equations, one from this term, one from this term, for any value of M2, which fits in essentially this much. So there are 2 equations, one of them is this, one of them is this. I won't bother writing them now. And you can check that. And you can find solutions for those equations.
Delta 2 of L was the anomalous dimension.
The anomalous dimension of the double field operator, high spin double spinful double field operator.
And delta 2 means epsilon squared.
Yes.
So Aninda, here you have fed in the anomalous dimension of phi from this Rishkov and tan kind of.
You don't have to do that. So you can actually go and say that there's a conserved stress tensor. So you can demand that. So what happens is that the anomalous dimension for this this looks like 1 minus 6 over L is 12 plus 1. And the fact that the anomalous dimension for L equal to 2 vanishes is because of this particular combination. So L in 12 plus 1. This 1 comes because of the anomalous dimension of steady phi. This guy. And this comes from this piece. Okay. So if you demand that there's a conserved stress tensor, you will fix that.
This is the surprising thing. I mean, you were just considering phi, the 4-point function of a scalar. I don't know the Lagrangian content of this theory. There could be, as I was saying yesterday, there could be Yukawa couplings with fermions. There could be all kinds of other stuff, and somehow still this, the del square phi equal to phi cubed is coming out of this. This delta phi is the same as what Rishkov and Tan found by using the equation of motion of this theory, right?
Yeah. So maybe the answer to your question is that I'll get additional solutions if I did not consider. So here I've set n equal to 1. So when you consider the gross this Yukawa coupling, I think you have to consider psi bar I.
What are the n?
ON. Yeah. And then so there's the psi bar. There is in the beta function there is some thing that depends on the number of flavors that you put in. So there's some global.
I can just have a single psi bar psi phi. I'm saying I don't know what this interacting conformal field theory is.
Okay, yeah.
How do I know that it's a Wilson-Fisher conformal field?
Can you give us one other example of something? The probability theory is near the free. So you say a scalar.
So I don't know. Is there some supersymmetric version of Wilson-Fisher in which it's still close to the free?
Yeah.
That's all I need. I need it to be close to the free field thing.
Yeah, I think it's just n equals 4 supercharges with the superpotential phi cube.
We'll also have this kind of
Which
right?
also has.
So then how do I distinguish between that one and this one?
The blocks will be different.
Well, I am considering only the phi scattering amplitude, and I'm deducing everything from there.
Yeah. Could it be that to leading order and epsilon it's the same?
But I see. That was relation to care.
Could it be that the leading order is actually, I don't know. For instance, in the case that we were interested in, what will the equation of motion? How will the equation of motion change?
So there will be, for example, del square phi equal to phi cube plus psi bar psi. So all this multiplicative combination technique which Rishkov and Tan use, it will be something different. It's some combination of phi cube and psi bar psi, which will be the secondary, and so on. I mean, the technique will certainly be different.
But do you know the anomalous dimension of this order?
No, I don't know. So one possibility is what Shiraz is saying, that maybe the anomalous dimensions continue to be the same.
Wait, the anomalous dimension. This is the anomalous dimension of phi bar of what? Of phi.
Phi itself, right?
Oh, in that case, the anomalous dimension should be 0, right? It's parallel.
So maybe there are solutions like that also, in which phi 1, phi 2, all of these guys are 0.
Right, because maybe I'm saying this wrong, but just check this. Suppose I take the Suppose I take the theory with 4 supercharges with superpotential phi cube. That gives me that would basically be scalar potential phi to the 4. Right, because del W by del phi is phi squared,
Right.
mod squared is phi to the 4.
Can you do that in itself? In actual terms?
I don't know. I don't really. I mean, this is the super. But these people have done super conformal. Your friends had some super conformal theories arbitrarily between 3 and 4, right? Yeah, I mean, Pentagon is Sheet short. The usual. I think so.
Super sorry.
I think so.
Can you define spinors in fractional dimensions? I thought there was some problem that the double cover was infinite dimensional.
I don't know how any of this is done, but I thought that it was somehow important that I remember a paper in which they made a big deal of the fact that SO2 is the same as U1. Super conformal algebra in 3 dimensions with 4 supercharges as SO2 R symmetry. The super conformal algebra in 4 dimensions with 4 supercharges as U1 R symmetry. For no other higher supersymmetry would these two be the same. Suppose you had double Zamano supersymmetry, it would be SO4 and SU2. These are not the same, but SO2 and U1 are the same, so somehow that will help to do some interpolation. But I should look up. Yeah, but in that theory, of course, phi would be a chiral operator. It's anomalous. It's anomalous dimension would be set by some number times R charge. R charge would be set by the fact that the super potential is phi cube. Right, because then the R charge has to saturate. So that should be then a protective operator, I think. Yeah, and I think probably be what you said, that basically the phi cube and the psi bar side will cancel.
So that possibility has to exist then.
So somebody should check for this is what I'm saying.
One thing that might happen is that the exchange operator. How can the exchange operator cancel to the leading term is this?
Well, it could just be that some of the assumptions you made about only one operator contributing, for instance, no longer true.
No, but I determine what is contributing at the leading order.
For instance, it suggests that psi bar side plays a role. Two spin zero operators. Somehow.
Two spin zero operators.
Because it suggests that phi mixes
Of
with
same dimensions. Oh, that is okay. That might happen. The two spin zero operators are the same, at least leading dimension.
You may have put in here somewhere that you know the spectrum of the theory in the field.
So that's delta phi. So delta phi begins at 1.
And
No, spectrum meaning
the full spectrum.
The full spectrum, including the fact that there's a phi square only that.
No, so I can determine what the dimension of the leading dimension of the exchange operator has to be.
So you got a 1 over n minus 2.
Yeah.
But that doesn't mean that only one operator.
That's true. That's what I was
of
saying.
that
Yeah, that's what I was saying. So there could be. I may need to put in 2 OP coefficients for different operators.
Phi square and psi bar side are
one is dimension 3, the other is
yeah.
2 and 1. Oh no, sorry, wait a minute, 4 dimensions. Sorry, 4 dimensions, 3 and 2.
3 and 2.
Yeah, psi bar side is the same dimension as phi cube.
Yeah. So it will not. That degeneracy is not there.
We could look at the anomalous dimension expressions.
So far as the phi cube kind of operator is concerned, it will come at some subleading order.
It will come at a more subleading order because phi cubed is 0 in the feature.
But those don't feed back into the coefficients of these guys, right?
They won't feed back into the coefficients of the dimensions, but then there is a C delta that is sitting there. So that knows about the OP coefficients.
Okay, maybe saying something stupid, but haven't you actually put in the information about the spectrum when you say that the pole should occur at h plus v?
No, that's not an assumption about the spectrum. That just follows from producing the same set of powers. That has nothing to do with the spectrum.
No, but that's the one is the definition of name. You can predefine. Oh,
Wait. Yeah, maybe you can just finish.
Yeah, okay. So the other thing that I wanted to show is what to do if you do the same analysis for numerics. That's again a much shorter code than what you would ordinarily write for any of these numerics, sophisticated numerics that people do. So if you do it in d equal to 4, so what people do is they plot what the allowed regions are. So there is the dimension of the seed operator, and this is the dimension of the next scalar that is there in the theory. And they say that the graph looks something like this. There's no analytic formula for the graph, this graph, and all these theories are allowed. So this is the line delta s equals to 2 delta phi. And in particular, they would say that anything above this would also something above this would also be allowed. Now, if you do the same analysis, which you can easily do with using the similar logic that you look at the. So if I write this entire thing as U, then you can look at these unitary blocks. You can plot what they look like, and for non-zero spin, it will turn out that they have a definite sign. You can play around with the blocks, but for spin 0, it can take on both signs, and it's needed to be able to solve that equation because these C deltas are positive. They are related to OP coefficient square. So the equation looks like this. So for the log term, you get some equation that looks like this. And in order to solve this equation, you require these to have both signs because these are positive. And then when you redo the analysis, it turns out that only a tiny sliver of this entire region is allowed. So it looks something like this, not this, and it lies below this line 2 delta phi. So then you conclude that there must be another scalar in the theory, but then the dimension of this scalar has to be less than 1 equal to 2 delta phi. You can determine this. This is not a straight line, so there's some form for this. And all this is obtained by just looking at this component. So if you look at more components, even stronger constraints will be formed. So maybe the hope is that again you start getting literally points of allowed conformal weak theories.
So that's the upper edge of the sliver. This delta S less than or equal to delta phi.
Yeah.
And then the lower edge is given by
some numerical solution which will involve this integrals minus I infinity to I infinity integrals that you're doing in the DNU channels. Instead of coming over the force because now we have a convergent integral.
Yeah.
I can just do the integral numerically between minus I infinity to I infinity in the DNU channel instead of doing the pole calculation. So yeah, so if it is indeed true that you start picking out only small regions of this, that will be great.
So even when you have at some higher order an infinite number of terms coming up, this implementing this is easier numerically than bootstrap, normal bootstrap thing.
Yeah, because I'm looking at just one component of the equation, which gives rise to this. You can look at all these components as well. So in ordinary normal bootstrap, you would do some linear programming, you would do something along those lines. But here, why it is easy is because in the T and U channels. So I said this channel, there is a simplification that only spin zeros contribute to the first component. Spin zeros and spin Qs to the third component. So, but in the T and U channel, I can just do the complex integral. Put it down in the box. Nice, numerically.
Could it be that, just going back to the question whether this is systematic, is it the case that spins, operators have higher and higher spins? No. I was just wondering whether higher operators pick up anomalous dimensions higher order than epsilon. But that's not the case, right? You already told us that.
Oh, you mean higher and higher? No, all operators so all these operators are the same. Square. But I square actually starts at epsilon. Anomalous dimension starts at epsilon. So these are morally like 5 square with some derivative.
But like 5 to the 4, where will it start?
5 to the 4 will start at order epsilon again. So there's some general formula. So the leading order anomalous dimension can be fixed using. So the anomalous dimension of this is n minus 1 divided by 6.
Okay, yeah.